go ahead and take a look at the hardness test. Now, the hardness test is a relatively simple and straightforward instrument. We basically take a tip of some type, a hard tip. This could be a sphere. It could be a pointed diamond shaped. There's various kinds of hardness tests. And the sphere or the tip of this machine could be made out of various materials, diamond being in a lot of the more modern instruments. And the basic idea is you take a sample and you would load it up to a specified load under the machine. And then after doing so, you would go back and you would measure the diameter of the hole that is left behind on the sample. And so these two samples here, if we were to just compare their images, we could say that the hardness of, and this is Brunel as Rockwell. If we compare these two samples, we could say the hardness of this, sample A here is going to be less than the hardness of this sample B. And we can tell that from the size of the indent. So there's a much larger indent here in the sample A as compared to B. You can also start to see in sample A around the edges of this indent that you're starting to get a little pile up. You can see sort of the plastic deformation. If you were to apply a much smaller load and a smaller tip, you can get much smaller indentations. But for these two samples, they're really too small to accurately measure. So that's the basic idea with the hardness test. It's relatively straightforward and it's relatively quick as a test. So there's a lot of different ones. There's the Brunel hardness, which uses steel or tungsten carbide spheres. And this is showing you the sphere that's used and then the hole that's left behind, the diameter of the hole that's left behind. So I guess to be consistent, I should have used a lowercase d in my last slide. But then you go ahead and you calculate this Brunel hardness value by simply taking the load and plugging in the values of the indenter size and the hole that was left behind. The Vickers case, so similar idea, except now it's got a diamond pyramidal tip. You can see it's a four-sided diamond. Again, you're going to go ahead and take a look at the hole that's left behind, and you're looking now at the diameter of this hole. The Knoop hardness, this one is designed for samples that sometimes are too brittle for the Vickers, and where the Vickers might crack the sample. The Knoop is a similar type, but now it's got this long axis. And so this allows you to measure at least this long axis as a hole on the surface, and you don't need to go as deep in order to be able to accurately see what you might with the Vickers. And so it's got also its own hardness equation here. And then Rockwell can use diamond cones or steel spheres, and it has various standard loads that are used. And in the Rockwell case, you're looking at the depth of the indenter. And I believe if you go ahead and take a look at the video that's posted in Canvas on hardness, it'll walk you through this Rockwell case. So there is the scale for these different hardness values. You can go convert from one scale to another. And some of these tests cover a much greater range of hardness values than other tests. So here's some Knoop hardness values just for comparison. Diamond, of course, is our hardest material that we have. That's why it's used as the indenter tip in many cases. 7,000 on the Knoop hardness scale. And if we go on down to something we're familiar with, like a window type glass, we're looking at a hardness of about 550. Okay. And then you're in the 2,000 ranges for the carbides, tungsten carbide, silicon carbide, boron carbide, aluminum oxide. And these are usually materials used in a lot of cases for grinding applications. So the value of the hardness test is that it's quick and it's easy. Most of these instruments are portable. So this means that you could put one of these instruments on a production line And then as a sheet or some other material that you're producing comes through, you could just place a small indent in the corner. In that sense, it's non-destructive, and you can get a quick measurement for hardness. And that's a quality check. If the hardness changes, then you know you've got a quality control problem. The other advantage of this is also that the hardness can be correlated with the tensile strength and the yield strength. But here we've got the case for the tensile strength, showing that if you were to do a Brinell hardness test, and these are the units that the Brinell hardness test comes out as kilograms per millimeter squared, and you multiply that by 3.45, you get tensile strength, a pretty good measure of the tensile strength of that material. Now this holds very well for the steels. That's where it's originally developed, although a lot of people use that number kind of blindly across different materials. You really shouldn't. And you can see here that depending upon whether you're looking at a brass or a cast iron, there are different slopes, different relationships here. So, but once that relationship's known, then you have a nice way of doing a quick test that you can correlate to tensile strength. Because otherwise you've got to take your material that you're producing, you've got to cut out a sample, maybe a dog bone specimen. You've got to take it to the Instron machine and mount it in the grips and run the test. It's a very, it takes more time. It's very time consuming, where this hardness test is quick. May take just a few seconds. All right.